Thank you everyone for being here for this presentation. Today I'm going to show you the changes to the synthetic module that we are introducing in the 2019.3 release. This updated synthetic module has a great new interface. It is also packed with substantial new features, and we hope our users will find these helpful when working with synthetic seismographs. But before I get to the demo, let me please give you a quick summary of the 2019.3 update, which drops in just a few more weeks. Apart from the new synthetic package, which we will get to in just a minute, we are also introducing our new auto-picking fault workflows. So you can now automatically detect faults in seismic data and then auto-pick them as surfaces directly into your interpretation. We've also added a few QC tools for faster analysis and interpretation of faults. There is also a major update to our geobody capabilities with a lot of additional features that we hope will really enhance the way you can use geobodies in your interpretations. There is a new tool for creating crossplots between seismic and attribute volumes or seismic data and well logs. We've updated our line balancing workflows, which is basically our mist eye analysis typically for 2D data. You will be able to pick and edit well tops from within the geophysics domain. We are introducing our first AI-driven workflow. This is a big thing for us, self-organizing maps-based waveform classification. Apart from these, as always, we made powerful additions and optimizations to our 3D visualization and many usability enhancements designed to make your workflows more efficient and increase overall productivity. So a lot of exciting things headed your way in 2019.3. Today's presentation, though, is all about our updated synthetic package. You've always been able to create synthetic traces in GVERSE Geophysics since forever using SynView. SynView had a simple workflow, let you quickly create and adjust synthetic traces using a variety of different analytical wavelets. This upgrade builds on the simplicity of SynView and adds a host of features key to creating a reliable synthetic and then tying it to your seismic. So what has changed, or to be a little corny, what's new with SynView? For starters, this has become this. You can see right off the bat it's a whole new user experience. It's much more modern, intuitive, gives you a lot of control over what you want to see and how you want to see it. All the options are housed either in the ribbons or these little buttons scattered around the app. It's all designed such that you don't have to look too hard to find what you need. There are no menus and dialogues to dig through or hidden options in right-click menus. Also, with this interface, you can open multiple synthetics in the same window, which makes comparing different wells or comparing the same well with different inputs much easier. But the look and feel is just one part of what we are bringing. We are also introducing a lot of new capability at almost every step of the synthetic creation process, starting with the input curves. From a log curve selection, so what log you want to use as your input sonic or your input density, we automatically select your sonic and density curves based on the aliasing you've already defined, but if you need to, you can select any other curve that you need. Similarly, what seismic you want to compare your synthetic to, we have very flexible options on what seismic data you want to view in the SynView window to compare your synthetic to. If you don't have a sonic or a density curve available for a well, you can estimate those. You can edit and process input curves, so things like blocking or smoothing your input. And if you don't fully trust your sonic curve and you have a more reliable TD table from, say, a check shot or a VSP survey, you can calibrate the sonic curve with that more reliable TD table for the synthetic creation process. Another big feature that we're adding, which I'm sure will make a lot of our users very happy, is the ability to work with deviated wells. You can now create synthetics for deviated wells within the new SynView. The next step is obviously the wavelet. We still have the variety of analytical wavelets that we've always had, and you can of course customize them to more closely match your desired wavelet. We've added a power spectrum tool to help you determine the parameters you want to use for your input wavelets. You can also import wavelets from external sources. If you want to use something that is more representative of your data, of your seismic, you can run wavelet extraction workflows. The new SynView can extract wavelets from the entire 3D volume or a 2D line. You can of course subset that spatially and also in time to get a more accurate representation of your zone of interest. You can also limit the extraction to within a certain radius of the well location, or specify the exact traces on a specific seismic section that you want to extract the wavelet from. So a lot of flexibility there. You can also use the wavelet editor to combine different wavelets together to get an averaged out wavelet, which you can then use to tie all your wells. So with the input curves and the wavelet, you get your synthetic trace. Of course, you then need to adjust the synthetic to tie it to your seismic. You can apply bulk shifts, stretch and squeeze the synthetic, do a multi-point adjustments, or use horizons and formations to do a quick auto adjust of your synthetic trace. We have interval velocity and drift curves that you can display to see if you're doing anything too funky with your adjustments. We also, of course, have full undo redo ability that we actually save in the database. So you can even turn off your computer, come back, and SynView will still remember the adjustments you made to the synthetic. A correlation tool compares the synthetic to your seismic and suggests appropriate time and phase shifts to best align the synthetic with the seismic. Alright, so just one additional note before we get into the demo. Everything I've talked about and I'm going to show you is included in the base package of GVERSE Geophysics. You don't need a separate license to access these features. Traditionally, these workflows have only been available with LogM, which is our advanced synthetic creation and modeling tool. But from 2019.3, these will also be a part of SynView that is included in the basic GVERSE Geophysics license. Alright, with that tidbit out of the way, let's get to the demo. Today for the demo, I will show you how to create a synthetic trace from scratch using the new SynView module. I have my interpretation open to my map, and the well I'm going to do this for is right here. I want to create a synthetic for this well, and to do that, I first have to open SynView. To get to SynView, I just right-click the well, and this could be from anywhere. The map view, or a 3D view, or a seismic section, basically anywhere that you can see a well. So I'm just going to right-click here on my map and choose the Create/Edit Synthetic option. The first thing I see is this dialog. You can think of this like a data selector. This is where I can choose which logs to use to build my synthetic trace and the seismic data I would like to compare it to. By default, SynView looks up the aliasing from GVERSE Petrophysics and finds the relevant sonic and density logs for this well and selects them as the input logs for creating the synthetic. And now with the new SynView, I'm not restricted to only using these aliased curves as my input. I can click on these lists here and choose whichever log I want as my input. My current aliasing scheme prioritizes logs named DT as the sonic, which is why this was already selected. If my aliasing was defined such that DT1, for example, was my favorite sonic log, then that's what would have been selected here. Also, you must have a sonic log to create a synthetic trace. SynView expects this curve, it is a requirement, but this requirement doesn't apply to your density log. If you don't have the density log, or it's just too unreliable because of the borehole conditions or whatever the reason may be, you can choose to create your synthetic using only your sonic. Just select the none option from the top of this list as your density log, and SynView will assume a constant density. The value of this constant really doesn't matter much because it just cancels out when calculating the impedance. You can also estimate the density from your sonic log. Click this button next to the drop-down and this will open the estimator. You can choose the input sonic curve and set the parameters for the Gardner's equation. Just click estimate. It's going to show you the estimated curve right here along with the actual input curve. If you want, you can change these inputs and parameters and keep running this until you get something that you're comfortable with. You can then save this and it will be selected as your input density log. The same process can be applied to your sonic log. If you don't have a sonic curve available but have a density log, you can estimate the sonic from density using this exact same process. Alright, so that's how we select our input logs. Let's keep it simple. I'm just going to use DT as my sonic and ρB as my input density log for creating the synthetic. The next section of the data selector dialog is where I can choose my seismic. The seismic I select here has no relevance to the actual creation of the synthetic. These traces that I select here are only for display. These are the traces that I would like to match my synthetic to when tying the well. Again, we have a lot of flexibility when choosing the seismic traces. I can choose the survey and version I want to use from the data tree. The well location on my selected survey is given right over here. This well falls on inline number 122 and crossline 54 for the selected 3D survey. You can choose to keep the well at the center and get traces from both sides of the well. That's what this number of traces option will do. it puts the well at the center and gets traces from both sides of the well for the selected inline or crossline. Alternatively, you can specify a range of traces that you'd like to compare the synthetic to. The well location relative to the crossline, since that's what I've selected right now, is given by this little symbol, and I can use the sliders to put this well exactly where I want it. You can compare the synthetic trace to 2D data instead of 3D if that's what you prefer. Just choose the 2D line you want to use. The exact location my well is projected on to this 2D line is given here, and just like for 3D seismic, I can choose to put the well at the center and get an equal number of traces from the left and right of the well, or I can specify a more precise start and end range of traces I want to use for my comparison. If you launch this window from a seismic section, this part of the dialog is pre-configured to select traces from the exact section here. So whatever section you had open, inline, cross line, or a 2D line, or even an ARB line, when you get to this dialog, those traces are already selected. This selection is already made for you to reflect the traces that got you here. For today's demo, I'm going to use my 3D data with 25 traces from the cross line passing through the well location to display alongside the synthetic and do my comparison. And once I have everything the way I want it, I can then launch the synthetic window. SynView opens with the synthetic trace already calculated using a default wavelet and displays that synthetic along with the input curve in seismic. It's as simple as that. If your aliasing is appropriate, you don't really need to do anything else, and you basically have your synthetic ready to be compared and tied to seismic in basically just a couple of clicks. Before we go on how to play with the synthetic trace and some of the other cool stuff, let me give you sort of a lay of the land as far as this window is concerned. You have the main synthetic display area with individual tracks containing the input curves, reflectivity series, the synthetic itself of course, and the seismic traces, etc. Right next to this is the parameter panel, which contains all of the parameters used to compute the synthetic. Finally, on the bottom left, we have the wavelet window describing the wavelet that was used for this particular synthetic. So these input curves and parameters are used to compute the reflectivity series, which is then convolved with this wavelet to get the synthetic trace. Now, log curve editing is one of the most important aspects to consider when creating a synthetic. I can do some basic editing and processing from right here within this window. If I want to smoothen my input logs, SynView lets me run a despiking algorithm from the processing window. To run the smoothing, I can just choose an operator length and depth range of the curve I want to smooth. If I don't want to apply to the entire log, I can choose the depth range here and then run the process. The results are displayed here, so we can take a look at the output of the process. If you want to do a few more iterations, you can keep going until you are happy with the results. Then give it a name, let's say DT Smooth, and save it. This curve, DT Smooth, will now be used as your input sonic. Another very frequently used process that we have available here now in SynView is blocking or upscaling the input log in an attempt to remove the high resolution information inherent in log curves and maybe get it to match more closely with the seismic resolution for a more realistic time. To do this, I just specify the number of layers I want my output to have and run the process. The blocked curve is displayed along with a comparison where the original and the process curves are overlaid one on top of the other to give us a better idea of how the blocking went about its business. Again, I can keep repeating this process until I am happy with the results. Let's add in a minimum thickness to the mix. Once I have something I like, I can save it. I'm going to call it DT Blocky. So now I can use this curve as my input sonic for creating my synthetic. These options are of course also available for your density log, so you can go in and apply the same processing to your density curve as well. With the sonic curve, there is one additional thing that is not available for density curves, and that is calibration. Let me switch back to my original sonic and open the calibration window. So if you have a check shot that you want to incorporate into the sonic curve, just choose that check shot here and hit calibrate. This will give you a comparison of the TD tables, interval velocities, and the drift along the calibrated sonic curve overlaid on the original curve. If you like what you see, you can save this and use the calibrated sonic for your synthetic computation. For now, I'm just going to disregard this and stick to my original sonic. Alright, so that's everything you can do with input curves, but that's only half the story. Perhaps even more important when creating a synthetic is what wavelet you use. And that's what we're going to take a look at next. By default, we use a Ricker wavelet with a center frequency of 35 Hz. But you can modify that and make it anything you want it to be. So it could be a Ricker with a different frequency, or a Butterworth, or even a wavelet extracted from seismic data. And we save these wavelets at the project level, so they're available across interpretations. I can create a wavelet for my interpretation, and it will be available for anybody else working in the same project. They can choose to use it or choose to use their own wavelets. It doesn't take very long to create a wavelet, but it's just another one of those things that you might not want to do every time you go in and create a synthetic for a well in your project. Creating a wavelet is simple. Launch the wavelet creator, choose the type of wavelet you want, set its parameters, give it a name, and click OK. And we have our wavelet. It shows up here in the wavelet panel, and the synthetic is instantly updated to reflect this new wavelet. If you want to look at the amplitude response, go to the amplitude tab, the phase tab. No prizes for guessing gives you the phase response. To compare the amplitude response of your wavelet with the seismic in your zone of interest, you can use the power spectrum tool. From the home tab, choose the seismic spectrum option. Select an area on the seismic, ideally in your zone of interest, and the spectrum is overlaid on the wavelet's spectrum, so you can see how closely the frequency content of your wavelet resembles that of the seismic. If I switch back to my default wavelet, you can see that the 35 Hz Ricker is quite similar to the seismic, at least in terms of frequency content. Okay, so analytical wavelets are nice and all, but detailed work usually requires wavelets to be extracted from seismic data. So it's more representative of the seismic you're trying to tie the well to. And like with everything else that I've shown you to this point, extracting wavelets in SynView is also very simple, very easy. Let's open up the wavelet extraction window. The first thing you must do here is specify the seismic you want to extract your wavelet from. You can do it from 3D volumes or 2D lines. You can do it at well locations, or just from the traces that you brought over to display along with your synthetic from the data selector. That's what this display traces option will do. I'm going to start off with the wavelet out of the 3D volume. This here lets me choose the data set I want to extract the wavelet from. If you have multiple surveys or more than one version of data available, this is where you can specify the data set you'd like to use for the extraction. We can also subset the volume, so I'm not required to use the entire volume for my extraction. The well symbols here give you the location of the well with respect to the seismic volume. They're there to serve as crude guides to how much of your volume you want to include in the extraction process. We don't expect you to be super precise with these sliders when trying to use just a couple of traces around the well location. We have a separate option for that, and we'll get to that in just a little bit. We can also subset in time to be closer to our zone of interest that we want to get the closest tie for. Let's just set that from 1000 milliseconds to 1500 for now. Okay, once we have our source seismic for the wavelet, you can then set other parameters associated with the wavelet, stuff like the wavelet length and phase, any taper that you want to use, and that's it. Click extract wavelet and it does its thing, and there is your wavelet. Let's give it a name, 3D wavelet, and save it. The wavelet is automatically set as the active wavelet, and now the synthetic that you see here was created using this new wavelet. So this was how to get a wavelet out of an entire seismic cube. But what about a more localized wavelet? How would we get a wavelet from seismic at the well location? The process is pretty much the same. Open up the wavelet extraction window again. This time I'm going to set the source as well location. Choose my 3D survey. I can also choose any 2D line that falls within this radius around the well. Let's subset this to the same region like we did the last wavelet. Click extract, and there's your wavelet, extracted from seismic at the well location. Let's call this well wavelet and save it. So both the wavelet from the seismic volume and that at the well location look quite similar at first glance. So how do I get a more real comparison? Well, for that we can open them up in the wavelet editor. Here you can see the wavelet I extracted from the well location, and the time, amplitude, and phase response is plotted here on the right. Now I can overlay other wavelets here on top of this wavelet. turn on the 3D wavelet, which was the wavelet that we extracted from our 3D seismic, you can now see exactly where it differs from the wavelet at the well location. Let's also add the analytical wavelet we started off with, just to see how that compares with our extracted wavelets. All the wavelets that I have displayed here simultaneously, I can calculate an averaged out wavelet for. So if I was, for example, working with 1, 2, or 10 wells, I can extract seismic wavelets at each well location and put them here and just calculate an average wavelet from those, and maybe get a more representative wavelet for all the wells I'm using in my interpretation. Okay, so now that I have a synthetic that is using the log curves and the wavelet that I wanted to use, I can go ahead and start tying it to my seismic. All the tools you need for that are located here in the well seismic tie ribbon. But first, let's reconfigure this display, this viewing area, to better assist us the tying process. From the Home tab, I'm going to get rid of the impedance track, and let's get rid of the density log as well. I'm working on a small screen, and I don't think I really need this right now. I'm going to add a drift curve so I can keep an eye on the changes I make to the synthetic. I'm also going to gain up the synthetic a little bit so we can see this better. This defaults to whatever display setting you have for your seismic, so you can make a real comparison, but you can control this individually as well. You can also display wiggles or the palette for both the synthetic and seismic, but I prefer working with the color palette only for the seismic and wiggles for the synthetic, so I have these options set to color for seismic and wiggle for synthetic. And before I start the tying, I'm just going to move the reflectivity track out of the way and get the drift curve next to the synthetic. I'm also going to make it wider so that I can detect subtle changes as well. Okay, so now that I have everything set up, I'm going to start tying my synthetic. The first peak that you see here, this formation right here, it actually should be down here next to this horizon. So I'm going to do a bulk shift, turn it on from the well seismic ribbon. On the synthetic, I click on the peak I want to move, and then on the seismic, I click on where I want to move the peak to, down to this horizon. 2 clicks and the synthetic is modified so that my peak is where I want it to be. This was a big shift that I applied, as you can see on the drift curve, but since it was just a static shift, it doesn't have any effect on the interval velocities, which obviously remain unchanged. Okay, so let's keep going down the track. And next, I want to line up this trough with this event here. I obviously can't do a bulk shift here because that's going to affect the first peak that I lined up. So instead of a bulk shift, I can stretch the synthetic to match these events. I will anchor the first peak I moved so that remains in place. The second click is on the trough I want to move, and the third click is on the seismic at the event I want the trough to move to. This stretches the part of the synthetic that lies between the first and second clicks, and the events line up without disturbing my previous tie. Let's do one more. This peak here, I can move this down to this event here. Again, I will anchor my previous pick, select this peak, and match it to the event on the seismic. If I do something crazy, I will be able to see the effect on the interval velocity and the drift curve. So if I, for example, really squeeze this part, you can see an unrealistic spike in the interval velocity straight away. And let's just undo that. In fact, let's undo the previous 2 edits as well, because I want to show you the multi-point stretch that can really speed up the tying process. So turn on the multi-point mode and then identify the events. This peak goes here, this trough goes here, and this one goes here. Double click to commit, and everything lines up. Open the correlation window to calculate the correlation between the seismic and the synthetic. You can even do an auto-calculate. You can even auto-calculate the time and phase shift that will give you the best correlation, and apply those changes to the synthetic if you want. I'm just going to skip that. Once you have everything lined up, you can commit this synthetic to the database, give it a name, and add as a new survey. And now you have your synthetic. So what do we write to the database? Well, pretty much everything. What logs were used, the wavelet, actual values of the logs, not just the names of the logs. We say the parameters, the shifts we've applied. Everything is stored so that you can recreate the synthetic exactly, even if the input logs or the wavelets used to create the synthetic are deleted or removed from the project. So this was an overview of everything that is going to be a part of SynView in the 2019.3 update. It truly is a complete synthetic package with a lot of features that you would need for your everyday sort of synthetic work, like the ability to edit your input curves, extract your wavelets, a variety of tools to quickly tie the synthetic. So everything you would expect a complete synthetic package to do. And as I mentioned earlier, this is part of the base package of GVERSE Geophysics. You don't need to purchase a separate license to use these features. So thank you very much for attending. If you have any questions or comments or things you'd like to see made part of SynView or other aspects of seismic interpretation, please feel free to reach out. And thank you once again.